All right, so first of all, we have to solve this structure for the reaction force. And it turns out you don't really have to solve it. I almost just whizzed right. I mean, I totally would have if Tim hadn't mentioned that you can stop after the first step of this. I would have just kept on chugging. But um, you have an upward force over there. You have a force vector over here. A horizontal force of 10,000. And so Newton's second law says 0 Fa plus Fbx Fby plus negative 10,000 0 is 0, 0. And the rotational equation, I'll do it about B. So we have a clockwise moment produced by Fa with a moment arm of 1, so negative Fa. And then this has a moment arm of 0.866, so we have 8660 equals 0. And then that's all you need. Fa is 8660. So now we can move on to the square-threaded screw problem with a force of 8660. Okay, so I think, to me, it's the clearest way to think about this is to think of everything on the screw being supported by this one block-shaped piece of thread. And this is the radius of the screw. And for the top of the screw to lift up, you need that block to slide up the incline. So there's that block-shaped piece of the screw. This incline has a, like this side, the height is given by the lead, and that was 0.01. And this side length is the circumference. So that's 2 pi times this radius, so 0.005. And that gives you an angle of 17 point, okay, I got 86. Okay, so now we want to take a free body diagram of the block. So what forces are acting? There's a straight vertical force of 8660, a normal force, a friction force that's parallel to the incline. Which way is the friction force pushing? Down, right? I'll just leave that here for now. And then there's a force pushing the block up the incline. And what's the direction of that force? Yeah, it's horizontal, totally horizontal. So it's not parallel to that incline. I'll call that Q. And if you think about like the fact that we're trying to find the value of Q right at the maximum of the possible friction force, okay? Like right before motion starts. This force of friction even though we're talking about static friction and you could have anything less than the maximum, we want to set it exactly equal to the maximum friction value here, right? So this is going to be 0.5, the coefficient of friction, times the normal, okay? Like you can't do that in every static friction problem, but you can do it in all the ones where you're trying to find the boundary between sliding and not sliding. Okay, I'm going to use a rotated coordinate system. So I have, if you think of the coordinate axes being here and here, I have q times the cosine of 17.86, which is 0.9518 q, and then negative q times the sine of that angle, so negative 0.3066 q. And then 8660 times sine and negative cosine, no, 8660 times negative sine and 8660 times negative cosine. So that's negative 2655.52, negative 8242.8. And then these two are aligned with the coordinate system, so you have negative 0.5 n, 0, and then 0 n. I'll just put them together. It's equal to 0, 0. And that gives you two equations for two variables. You can solve that as a matrix equation. And I got Q equals 8487.06. And N, you have to get to 844.9. But this is the one that matters. And now the torque about the screw is equal to Q times the moment arm that it has. So that's 8487.06 times the radius of 0.005, and you get 42.44 Newton meters. And then that torque is also equal to the applied force at the lever times the moment arm of the lever, which is 0.4 in our case. So that gives you that the force you have to apply to the lever is 106.1. Any questions on that? Yep.
You always have to go to the torque and then come back out to the force. Like you can't.
You could come up with, I guess, an equation. You could just combine those equations, I suppose, right now and do it. But depending on, I do it this way because it's easier to remember, you know. And depending on which one of those variables you have to solve for, instead of thinking of it as a bunch of formulas, just think of it as a torque that in each case is a force times a lever arm, you know. So I guess next time we'll do one bearing problem and then we'll move on to virtual work.